Thanks for the introduction. I'm going to talk to you about improving the current practice of DDoS defense using new networking technologies such as software-defined networking and network functions virtualization. I'll describe the design of Bohatei, which is a DDoS defense platform that we built with my colleagues at Carnegie Mellon and Illinois, and we've made its implementation code also available. So DDoS attacks impose a huge cost on their victims, which is both monetarily cost, with a cost of tens of thousands of dollars an hour, and also damage to the reputation of the target. So just a couple of weeks ago, the FBI warned of an increase in DDoS extortion scams. And unfortunately, recent trends are just suggesting that things are getting worse. So first, we see an increase in the number of attacks. For example, 30% of botnets attack more than 50 targets a month. Another trend is that we are observing huge attacks. Now, attacks of hundreds of gigabits per second are becoming the new norm. And finally, we also see an increase in the diversity of attacks. Both new types of attacks are emerging, such as NTP attacks and many others. And also, we see new variations of known attacks, such as tsunami scene floods. So given this landscape, what are we actually doing today about DDoS attacks? So today we rely on proprietary hardware appliances for DDoS defense. And what this means is essentially we buy these appliances that are quite expensive and come with a fixed functionality and capacity and put them at fixed locations in the network. And it turns out this current practice has serious limitations. First, these appliances have a fixed functionality. So if I buy a blue box, it is only good for attacks of type blue. So if I get other types of attacks, orange or red, at that point we are helpless. And we are at the mercy of the appliance vendor to provide us with new defense capabilities. Another limitation of the current approach is that these appliances have a fixed capacity in terms of the volume of attack they can handle. So imagine we have a scenario that is shown here. So the x-axis is time and the y-axis is the attack volume. So because the capacity of the device is fixed, that is shown as a horizontal line here, so most of the time we end up in one of the two unpleasant situations. If the capacity is more than the actual attack volume, we are essentially wasting defense resources. On the other hand, if the attack volume exceeds the capacity, now the attacker succeeds in delivering the attack to the customer. So either way, we are in an unpleasant situation. And finally, because these appliances are expensive, we typically buy only few of them and put them in fixed locations in a network. And what that means in terms of traffic processing is that now we have to deviate traffic sometimes from its optimal path just to make sure that it goes through these appliances. So this causes extra user-perceived latency and also requires complex routing hacks to enforce, which is by itself an error-prone procedure. So given these limitations, our vision here is to enable flexible and elastic DDoS defense. So what do I mean by that? So first, we want to have flexibility with respect to attack types. So I want to be prepared to defend against different types of known attacks, whether it is the type blue or orange or red, depending on the current attack scenario, I want to be able to defend. We also want flexibility with respect to the attack location. So suppose in our network there are 3 ingress points from which the traffic can enter our network, ABC. So I want to have the flexibility to launch my defense capability wherever it is needed, depending on the current attack scenario. And finally, what we need is elasticity, which means I want to be able to elastically scale my defense capability proportional to the volume of attack, again, depending on the current attack scenario. So now what is Bohatei? So Bohatei is a practical ISP scale system that we've built for flexible and elastic DDoS defense. And it uses SDN and NFV. And it can actually react to attacks of 500 gigabits per second in 1 minute. So before I talk about the design of the system, I'd like to give you a little bit of background on SDN and NFV because these are the technologies that you may or may not have heard of. So what is SDN? SDN, or software-defined networking, is a pretty recent trend in networking. And the motivation for that is traditionally we use for networking, we use distributed routing protocols to enforce whatever forwarding behavior that we have in mind. And it turns out to be a very complex and error-prone procedure. So over the past years, large enterprises have started to move to what is called SDN, which essentially says, let's get rid of all this distributed intelligence, which is tightly coupled with the data plane. And now let's just use a logically centralized controller that centrally programs the forwarding behavior of the switches. And on top of that, we can implement whatever forwarding logic that we want in a very flexible manner. And in fact, a lot of large companies have already rolled out SDN deployments. On the other hand, another trend is network functions virtualization, or NFV. And again, there is a historical motivation for that, traditionally we use these standalone and specialized hardware appliances for different purposes, for firewalling, intrusion detection systems and whatnot. And they are very inflexible, they have very narrow APIs, and they are expensive. So recently, again, companies have started to break away from this approach and start using commodity hardware. And the idea is that now on top of this commodity hardware, we can just launch VMs of appropriate types that we need. So essentially, the function becomes a virtual machine here. And we can essentially scale depending on the capacity we need just by spawning new VMs. So why do we care about these two things? Because we think they are useful for DDoS defense. So first, if you think of it as NFV, it essentially brings down the cost by replacing specialized hardware by commodity hardware. It also potentially enables more flexibility with respect to functionality, because now we are replacing hardware with software, which is inherently faster to innovate and replace. And also, NFV enables elastic scaling of defense, potentially, because now, depending on the attack scenario, we can simply launch more VMs. So that is how we can scale, as opposed to the fixed capacity of appliances today. And on the other hand, SDN gives us the flexibility of routing the traffic the way we want through the intended sequence of virtual machines, depending on our defense policy. So essentially, our work is about bringing the benefits of NFV and SDN to the context of DDoS defense. So next, I'm going to give you an overview of Bohatei and the challenges we face before we can make it real. And by the way, the word Bohatei in Japanese means breakwater that are used in the real world to defend against tsunamis. So this is our vision. We envision a world where ISPs provide their customers with DDoS defense as a service. And in fact, ISPs have already figured out how to monetize a lot of other services. So DDoS defense could be just another service. And the way it works at the high level is that the ISPs start with a set of defense policies. That is our intention of dealing with different types of attacks, and I'll tell you about it more later. And it uses SDN and NFV to make sure that suspicious traffic goes to data centers, and over there, it goes through the intended sequence of virtual machines as mandated by the policy. So at the high level, we need a three-stage workflow to make this vision real. So first, we need a strategy layer. And the reason for that is because any real system has a non-zero lag. So we need to be able to predict the attack scenario for which we are getting prepared. And so here we need a prediction mechanism to be able to predict the attack pattern that are coming up. And then given these predictions, we need a resource management module that decides about the number of VMs, types of VMs, and the locations where we want to launch these VMs, and also the routing policies. And finally, we need to actually enforce these results by a network orchestration mechanism that essentially configures the switches across the ISP to make sure that the traffic is being treated the way mandated by the resource management module. So we consider a general and dynamic threat model. And what it means is the attacker can target one or more of the customers of the ISP. And we assume that the attacker has a fixed budget with respect to the maximum volume of attack it can launch at any given time. So it is not unbounded. And then given this budget, it has a lot of flexibility. It can pick its target, it can choose the attack type, it can choose the volume of attack, and also the ingress points from which the attack traffic enters the ISP. And it can adaptively change its behavior with respect to these dimensions constantly. So because of this threat model, it turns out the workflow that we envision is not necessarily easy to realize. So first, because the adversary is dynamic, it can strategically change its attack patterns to surprise our system by tricking us in predicting the wrong thing. So we need a resilient strategy to predict attacks. The second challenge is that we need a fast way of resource management, because if we spend a lot of time for resource management, by the time we are done, we could be facing a very different attack scenario, which is not practical. And finally, as I will discuss, it turns out if we just use SDN naively, it's not going to scale to a scenario involving DDoS traffic. So we need a scalable mechanism while using SDN. So I'm going to walk through each of these three challenges and tell you how we addressed each of them. So starting with resource management. So by the way, we have a lot of details in the paper, so here I'm hoping to just give the high-level idea. So in resource management, what we are doing is we use the defense library and the available compute and network resources and our prediction of future attacks to decide about our posture, the number, location, and the type of VMs, and also the routing decision across the ISP. And you can imagine this can be formulated as a global optimization problem, and in fact that is correct and optimal. But even for decent-sized ISPs, it takes hours to solve. This is not practical. So to solve this problem quickly, first we decompose the problem in a hierarchical manner. So first, we just use coarse grain information from the data centers to decide how much traffic to send to each data center from each ingress point. And then at this point, each data center locally solves its VM assignment problem in parallel with others. So the combination of these fast, greedy algorithms and parallelism in the second stage will give us a huge speed up, as I will give you numbers in the evaluations. So the second question was, how do we orchestrate the network in a scalable manner? So first I'll tell you what is the problem if we use SDN naively. So to be concrete, the example here is that we have a policy that says the green packets should be sent to VM2 and the red packets should be sent to VM3 because of whatever defense policy that we have. And then the way SDN works, whenever an SDN switch gets a packet that belongs to a flow that it hasn't seen before, it needs to send it to the controller to learn the corresponding forwarding rule. And this happens per new flow. And this is just fine in benign scenarios, as people have used. But this is actually itself a vulnerability in case of DDoS scenarios, because now all an attacker needs to do is to craft traffic that involves a lot of distinct flows. And the result of that will be, first, the control channel between the switch and the controller will be overwhelmed. And also, the switch rule space, which is limited, will be quickly exhausted. So we cannot just use SDN naively. So our idea to address this scalability limitation of SDN is to use proactive tag-based steering. So going back to the same example, first, the controller proactively, and before any traffic arrives, will configure the tagging behavior of the virtual machines. In this case, it's instructing VM1 that, oh, if you see traffic that is benign, before sending out the packet, put the tag value of 1 in the packet. If it is suspicious, put the value of 2. And the controller also configures the switch in terms of these tag values. So now the switch simply looks up the tag values and will decide about the next hop VM that it needs to forward the packet to. So we have gained two advantages here. First of all, the setup is proactive, so there is no real-time interaction between the control plane and data plane. And also now, if you look at the switch forwarding table, the number of rules is proportional to the number of next hop VMs as opposed to the number of distinct flows. So the combination of these two ideas of proactiveness and per VM tagging makes the orchestration scalable. So finally, let's look at the problem of predicting attack scenarios. And first, what is the challenge with that? So essentially, like I said, any real system has non-zero lag. So we need to be able to predict attack scenarios. And if we do this naively, the adversary that we have modeled can easily game the system by making us over-provision, in which case we waste resources, or under-provision by underestimation, in which case the attacker will succeed in getting the attack traffic to the target. So in the example here, the x-axis is time and the y-axis is the attack volume. And if we do something very simple for prediction, maybe we say, okay, in the past we saw SYN flood, in the past 3 time epochs. So maybe also in the next time epoch T4, the attack type will be SYN flood, and its volume probably will be the average. It looks kind of reasonable. And in this case, a smart attacker can send us a very different type of attack, maybe DNS amplification attack, at a very different volume. So we essentially are not prepared for this at all. So the message here is that any simple prediction can be gamed. So what do we do about that? So first, we define regret to be able to evaluate the goodness of different prediction candidates. So the regret essentially numerically represents how worse we did in our prediction with respect to the best static strategy in hindsight. Because in hindsight, of course, we can do perfect prediction. So it's just a baseline to evaluate. And then what we do is we borrow ideas from a framework known as follow the perturb leader. And using that, we design an online adaptation algorithm to predict attack scenarios. So again, the details are in the paper, but the high-level idea is that to predict the attack scenario, not only should I use the past data, but also I need to factor in a random noise component. And the property of random noise component is that it sort of makes it impossible for the attacker to deterministically defeat the system. So to put everything together, these 3 design components, we start with the past data and using this online adaptation algorithm to predict the attack scenario. We feed that information to the hierarchical and fast resource management that also uses defense policies to decide about the number and location and type of VMs and routing policies. And finally, the scalable tag-based orchestration is in charge of actually launching VMs and setting up traffic forwarding rules across the ISP. And in effect, what happens is that now we are prepared. When the attack comes, we send it to the data center, and it will go through the intended sequence of VMs optimally. So I'll tell you a little bit about the implementation of the system. So I mentioned about the defense policy library, and what this policy library is essentially it is a set of defense graphs. And we can think of each graph as an interconnection of logical defense modules that we can put together as we wish, depending on our knowledge or whatever policies that is available. So this is just a very simple example based on known techniques, just to give you an idea of what we can do with this framework. So here for SYN flood attacks, what we are doing is first we use a module that simply counts the difference between the number of SYN packets and SYN ACK packets on a per source basis. And if its difference is huge, it decides it's an attack, it's attack traffic. So it will send it to the next hop VMs that are log and drop. If the difference is very small or 0, it is okay, so we'll send it forward. And if it is in the gray area, maybe we are not sure, so we send it to a SYN proxy for further processing. And we've implemented a few of these defense libraries based on known techniques, so we don't have any innovation here, and use open source tools to realize this. So now our actual end-to-end framework, in the control plane, we are building on top of Open Daylight, which is an industry-grade platform for SDN control. In the data plane, which is the actual network elements, we have switches based on Open vSwitch, and the defense VMs are based on open source tools such as Snort, IP tables, and Bro. And in terms of APIs between data plane and control plane, first we use OpenFlow, which is already a popular set of APIs for programming SDN switches. And also we use what is called flow tags, which is based on our prior work to enable tagging operation that is something we use to scale the system, as I described earlier. So they all run on top of KVM, and we did our evaluations on top of a 13-node cluster on our campus. And for larger attacks that our physical network could not handle, we augmented those with simulations. And we've made the implementation code available. Okay, so having all this, I'm going to give you a few sample results of our evaluations, and there is a lot more in the paper. So we are interested in 3 types of questions. First, is the system fast? The second is, can it actually handle very large attacks? And finally, the question is, can it effectively cope with dynamic adversary that strategically change the attack pattern? So first, speed or responsiveness. So we evaluated our hierarchical resource management scheme, and it just takes a few milliseconds as opposed to hours that it would take to solve the problem optimally. And the good news is we are losing less than 1% in terms of optimality. Then we want to see how the end-to-end system reacts in terms of speed to attacks when they are launched. So the x-axis here is time, and the y-axis is the throughput of benign traffic. So in case of each attack type, at the 10th second, we launch the attack. And what we want to see is how fast we can recover the throughput of the benign traffic back to where it was before the 10th second. And what we see here is that Bohatei can restore the throughput of legitimate traffic in about a minute. The second question is the scalability. And what I'm showing here is the x-axis is the attack volume, and the y-axis is the number of switch rules. And we are comparing Bohatei with a naive SDN implementation that uses per flow forwarding rules. And the message here is that the per VM tagging idea cuts the number of forwarding rules by 3 to 4 orders of magnitude. And there is another plot I'm not showing here, but the result of that is our proactive setup, as opposed to naive SDN reactive setup, reduces the switch forwarding rule setup time by 3 to 4 orders of magnitude. And finally, we evaluated in practice to see how resilient the system is against adversaries that change the attack type strategically. So what we learned here is that across a range of different models of adversaries, Bohatei's online adaptation algorithm gains the minimal amount of regret. So in this case, on the x-axis, I'm showing different models of adversaries. For example, the first one, rand ingress, is essentially in each type epoch changing the ingress points of the attacks at random, but doesn't change the attack type. Similarly, we have other models of adversaries. And we have 3 types of prediction algorithm. 2 of them are very simple, uniform, and based on previous epoch. And one is Bohatei, that is the online adaptation. And what we see is that the Bohatei's algorithm consistently gains the minimal amount of regret. So by the way, this plot is regret with respect to successful attack. We have similar results that I'm not showing here with respect to the resource that the system would waste. Okay, so to conclude, we saw that today's DDoS defense has serious limitations in terms of cost, lack of flexibility, and lack of elasticity. And what we do in Bohatei is to bring the benefits of SDN and NFV to make DDoS defense flexible and elastic. It turns out it is not straightforward. There are 3 challenges of responsiveness, scalability, and resilience against dynamic adversaries. And we had 3 ideas to solve this: hierarchical resource management, proactive tag-based forwarding, and an online adaptation strategy. And we learned that the system is scalable and can react to very large attacks very quickly. And looking forward, we believe that similar ideas might be applicable to other security domains that suffer from similar symptoms today. Thank you.
Steve Checkaway, University of Illinois at Chicago. So this is great work. So the question I have is while you were testing your system against adaptive adversaries, do you have a sense of which attacker behavior performs best?
So I think what we saw here is that the attackers have 3 dimensions of flexibility in terms of type and volume and ingress of attacks. And what we learned is if we make mistakes in prediction with respect to any of these 3 dimensions, our posture will be ineffective. Okay. So we need to do a good job on the 3 dimensions.
Thank you. Any other questions?
Yeah, so I think we are essentially a constant factor away from that. We tried up to 500 gigabits per second, so I believe it is not unrealistic to think of defending against terabyte attacks. Okay. All right. Thank you.